Chapter 5. Control Valve Selection.
Next, we turn to valve selection basics.
I would like to introduce the starting point of control valve selection. Control valves handle all kinds of fluids, from the cryogenic range to high temperatures exceeding 1000 degrees Fahrenheit, or 538 degrees Celsius. Therefore, the core of selection is to optimally combine the valve body style, material and trim construction design to suit the intended service conditions. In addition, the required flow capacity and the system's operating pressure range must be considered to ensure satisfactory operation without undue initial expense. In this process, reputable manufacturers and their representatives actively help in finding the valve most appropriate for the existing service conditions.
Because there are frequently several possible correct choices for an application, sufficient information must be provided without omission for accurate selection. First, the type of fluid to be controlled, as well as its temperature, viscosity, and specific gravity are required. Next, the required flow capacity must be presented with both maximum and minimum values, and the valve inlet and outlet pressures must also be specified for both maximum and minimum. Pressure drop should be provided separately for normal flowing conditions and for the shutoff state. If noise is a critical factor, the maximum permissible noise level and its measurement reference point must be included, and if the degrees of superheat or the existence of flashing are known, these must also be communicated.
Now, I would like to introduce the specifications regarding piping, materials, operation methods, and signals. Specify the size and schedule of the inlet and outlet pipelines, and provide any required special tagging information. The valve body material is designated by standards, such as ASTM A216 grade WCC, A217 grade WC9, or A351 CF8M. End connections and valve ratings are detailed in forms such as screwed, Class 600 RF flanged, or Class 1500 RTJ flanges. You must determine the desired action on air failure, whether the valve should open, close, or retain the last controlled position, and verify if instrument air supply is available. Finally, the instrument signal is specified as 3 to 15 sig, 4 to 20 milliamperes, heart, etc. In addition, there are further items that require agreement between the user and the manufacturer depending on purchasing and engineering practices.
Next, I would like to introduce the valve configuration items that must be agreed upon by the user and the manufacturer. Determine the valve type number and size, and select the valve body construction from options such as angle, double port, or butterfly. For plug guiding, distinguish between cage style and port guided, and for plug action, decide between push down to close or push down to open. Determine whether the port size is full or restricted, and decide on the valve trim materials. Determine if the flow action tends to open or close the valve, and calculate the required actuator size accordingly. The bonnet style is chosen from options like plain, extension, or bellows seal, and packing materials are selected from PTFE V-rings, laminated graphite, or environmental sealing systems. Finally, determine the necessary accessories, such as a positioner or hand wheel. Some of these options were covered in previous chapters, and the rest will be explored in this and following chapters.
Now, I would like to introduce the actual valve selection procedure. The first step is to determine the service conditions, finalizing the inlet pressure P1, differential pressure delta P, flow rate Q, inlet temperature T1, as well as fluid properties and allowable noise levels. Based on these determined conditions, select the appropriate ANSI pressure class required for the valve body and trim. Next, calculate the required CV, the preliminary flow coefficient, and check the noise and cavitation levels during this calculation process. Depending on the results of this check, you will proceed to the trim type selection stage.
I would like to introduce how to choose the trim type. If no noise or cavitation indications appeared in the previous step, you can select the standard trim. On the other hand, if aerodynamic noise from gas flow is high, apply whisper trim. And if noise from liquids is high or cavitation is expected, select Cavitrol 3 trim. The key is to apply different trims based on whether the noise originates from gas or liquid, and whether cavitation occurs.
Now, I would like to introduce how to finalize the valve body and trim size. The core is to choose a body and trim size that satisfies the required CV calculated in the previous step. At this time, you must not only match the CV but also check the travel, which is the distance the valve plug moves, the trim group, which is the set of trims available for that body size, and finally, the shutoff options to determine the allowable leakage. Since the trim group limits the available trim materials and configurations for each body size, whether the desired material is within that group will be reviewed again in the next step. The shutoff class determines the allowable leakage when the valve is closed, so it must be matched to the isolation requirements of the process.
Following this, I would like to introduce the selection of trim materials. Choose trim materials that suit the fluid conditions of the application, but the most important point is to verify that the selected trim is actually available within the trim group for the previously determined valve size. If the desired material is not in that trim group, you must look for another material or return to the body size selection stage for reevaluation. The corrosiveness and erosiveness of the fluid, along with temperature conditions, serve as the basic criteria for determining the material.
Next, I would like to introduce the review of options and the selection criteria for the valve body material. In the final stage of valve selection, additional options such as shutoff class and stem packing are reviewed. The selection of the body material is typically based on 4 factors. First, operating pressure. Second, temperature. Third, the corrosion properties of the flowing fluid. And fourth, its erosion properties. These 4 factors serve as the basic starting point for determining which material to use.
I will now discuss the trade-offs and economic considerations when choosing a body material. Since it is not easy to find a material that satisfies all 4 factors, pressure, temperature, corrosion, and erosion, a compromise is often necessary. For example, even if a material has excellent erosion resistance, it may not be suitable for a specific application if its corrosion resistance is poor when handling a particular fluid. Some service conditions require the use of exotic alloys or special metals to withstand the strong corrosive properties of the fluid. Because these materials are much more expensive than common metals, economy also becomes a factor that cannot be ignored in material selection.
This slide provides a detailed introduction to the table pairing the casting designations and wrought equivalents for high-nickel alloys. The table consists of 4 columns: casting designations, equivalent wrought trade names, generic designations, and UNS numbers for wrought equivalents. Looking at the stainless series, CF8 is 304 stainless with unions S30400, and CF3 is 304L with S30403. CF8M is 316 with S31600, CF3M is 316L with S31603, and CG8M is 317 with S31700. In the high alloy section, CK3MCUN is alloy 254, trade name 254 SMO with S31254, and CN7M is alloy 20, Carpenter 20CB3 with N08020. CW2M is new Hastelloy C, namely alloy C276 with N10276. CX2MW is Hastelloy C22, alloy C22 with N06022, and CW6MC is Inconel 625, alloy 625 with N06625. CY40 is Inconel 600, alloy 600 with N06600, and CZ100 is nickel 200, alloy 200 with N02200. In the Monel series, M35-1 is Monel 400, alloy 400 with N04400, and M25S corresponds to S Monel. For carbon steel casting designations, WCB is J03002 and WCC is J02503, while for low temperature use, LCB is J03003 and LCC is J02505. The footnotes at the bottom of the table indicate that Avesta 254 SMO is a trademark of Avesta AB. Carpenter 20CB3 is from Carpenter Technology. The Inconel and Monel series are from Special Metals, and Hastelloy is from Haynes International.
Finally, I will introduce the commonality of cast carbon steel bodies and the ordering specifications for high nickel alloys. The alloy table from the previous slide concludes with the Haynes International Trademark footnote. In practice, since most control valve applications handle relatively non-corrosive fluids at reasonable pressures and temperatures, cast carbon steel is the most widely used body material. This material provides satisfactory service at a much lower cost than exotic alloys. Meanwhile, separate specifications have been developed for ordering high nickel alloy castings with very high corrosion resistance. These specifications contain solutions to problems previously encountered with those alloys, such as poor corrosion resistance compared to wrought materials, poor weldability, and lack of casting integrity. The relevant designations are organized under the designations for the high nickel alloys title and the generic designations column of the table.
I would like to explain that high corrosion-resistant cast materials, such as high nickel alloys, require separate and strict specifications from the ordering stage in valve body material selection. In the past, these alloys had issues such as lower corrosion resistance than wrought materials, poor weldability, insufficient casting integrity, and long lead times. To resolve this, ordering specifications include foundry qualification, dedicated pattern equipment, pattern alloy qualification, and heat qualification, as well as detailed control regulations for raw materials, visual inspection, weld repairs, heat treatment, and non-destructive testing, or NDT. A list of these exotic alloys is organized in the designations for the high nickel alloys table in the handbook, and the following descriptions and tables provide basic information on various castable materials used for valve bodies along with ASTM material designations.
Next, we turn to material and ratings.
I will now introduce that when writing material specifications, especially for pressure-containing parts, using the correct ASTM designations is considered good practice and is encouraged. Additional engineering data on materials is organized in Chapter 10. The most widely used body material is cast carbon steel, ASTM A216 grade WCC. WCC is most commonly used for moderate services such as air, saturated or superheated steam, and non-corrosive liquids and gases. However, it is not used above 800_X0001_F for 27_X0001_C because the carbon-rich phase may be converted to graphite. It can be welded without heat treatment unless the nominal thickness exceeds 1¼ in 32 millimeters. The standard class pressure temperature ratings for this material follow the ASME B16.34 standard.
This chunk corresponds to the title of the pressure temperature ratings table for standard class WCC valves. The table itself targets ASTM A216 grade WCC valves and is prepared in accordance with the ASME B16.34 standard. The core of this table is to show the so-called derating relationship, where the allowable working pressure for each class decreases stepwise as the temperature rises. The baseline lowest temperature range is -20 to 100 degrees Fahrenheit, or -29 to 38 degrees Celsius, and the highest working pressure is allowed in this range. When using the table, you can check the maximum working pressure the valve can withstand under those conditions by reading the value where the row corresponding to the actual service temperature and the column for the selected pressure class meet.
Now I would like to introduce ASTM A217 grade WC9, which is a cast chromium molybdenum steel. WC9 is the standard chromium molybdenum, or CRMO grade. It has taken the place of the former standard C5, because it offers superior casting and welding properties. In fact, it has successfully replaced C5 in most applications, showing great performance especially in steam and boiler feed water service. The working pressure ratings are provided in SIG for each pressure class.
I'll now introduce the pressure temperature ratings table and high temperature characteristics of WC9 valves. Based on ASME B16.34, the baseline temperature range of -20 to 100 degrees Fahrenheit allows 1500, 2250, and 3750 SIG for each class. As the temperature rises, these values gradually decrease to 1455, 2185, and 3640, and eventually drop to 1015, 1525, and 2540. According to the table footnotes, the minimum rating of 20 sig, or 1 bar, applies only to welding end valves, and flanged end ratings terminate at 1000 degrees Fahrenheit. Chromium and molybdenum provide erosion corrosion and creep resistance, allowing use up to 1100 degrees Fahrenheit, or 593 degrees Celsius. However, WC9 requires preheating before welding and heat treatment after welding.
Next, I'll introduce the C5 material, specifically ASTM A217 grade C5, among cast chromium molybdenum steels. In the past, C5 was commonly specified for applications requiring chromium molybdenum steels. However, this material has the weakness of being somewhat difficult to cast and having a tendency to crack when welded. For these reasons, WC9 has taken over the standard position from C5. Valve ratings are presented in a table summarizing the working pressure by class and sig, which is referred to as working pressure by class.
The pressure temperature ratings for C5 valves are organized based on ASME B16.34. In a range of minus 20 degrees Fahrenheit to 100 degrees Fahrenheit, or minus 29 degrees Celsius to 38 degrees Celsius. The working pressures are 1500, 2250, and 3750 sig by class. As the temperature increases, the ratings gradually decrease, starting from 1490, 2235, and 3725, then dropping to 1430, 2150, and 3580, and then to 1410, 2115, and 3530. In higher temperature ranges, they take values such as 1330, 1995, and 3325, 1210, 1815, and 3025, and 1135, 1705, and 2840. In the highest temperature range, it concludes with values of 1450 and 2415, 1110 and 1850, and finally 1370 and 20 sig. According to Note 1, the 20 sig value applies only to welding end valves, and flanged end ratings terminate at 1000 degrees Fahrenheit. Meanwhile, although WC9 has replaced C5 in many applications, C5 continues to be used in refinery applications because its higher chromium content provides better resistance to high-temperature sulfidic corrosion.
Next, I'll introduce cast type 304L stainless steel, or ASTM A351 grade CF3. This material is a good choice for chemical service valves and is particularly suitable for certain chemical service applications, including nitric acid. A major advantage is that optimum corrosion resistance is retained even in the as-welded condition. Looking at the pressure temperature ratings, in the range of minus 29 degrees Celsius to 38 degrees Celsius, the ratings are 1440, 2160, and 3600 sig by class. As the temperature rises, they decrease to 1200, 1800, and 3000, and then to 1080, 1620, and 2700. In high temperature ranges, they take values such as 1490 and 2485, 1395 and 2330, 1310 and 2185, 1290 and 2150, and 1275 and 2125, and continue to 1245 and 2075, and 1210 and 2015 at higher temperatures. In the highest temperature range, values such as 1605, 1545, and 1285 appear, along with the 20, 15, and 10 sig values corresponding to Note 1.
Now, I'll introduce cast type 316 and type 317 stainless steels. First, to revisit Note 1 from the previous table, those values apply only to welding end valves, and flanged end ratings terminate at 1000 degrees Fahrenheit. ASTM A351 grade CF8M is the industry standard stainless steel body material corresponding to type 316. Because molybdenum is added, it has greater resistance to corrosion, pitting, creep, and oxidizing fluids compared to type 304. It also has the widest temperature range of any standard material, usable from minus 425 degrees Fahrenheit or minus 254 degrees Celsius, up to 1,500 degrees Fahrenheit, or 816 degrees Celsius. Rough castings undergo heat treatment to achieve maximum corrosion resistance. Meanwhile, type 317 or ASTM A479 grade UNS S31700, is essentially S31600 with the nickel and molybdenum contents increased by 1% each.
I would like to continue introducing the characteristics of S31700 material. As a result of increasing nickel and molybdenum by 1% each, the resistance to pitting is improved compared to S31600. Like S31600, S31700 is completely austenitic and non-magnetic. Because its strength is similar to that of S31600, the same pressure temperature allowances apply. For reference, as the CF3 table continues, the ratings for the range of -29 to 38 degrees Celsius are listed as 1440, 2160, and 3600 sig. Meanwhile, CG8M is the casting version of S31700. It contains 15 to 35% ferrite and is therefore partially or strongly magnetic. In general, type S31700 has better corrosion resistance than S31600 in certain environments due to its higher molybdenum content, and it shows excellent resistance to digester liquor, dry chlorine dioxide, and many other pulp and paper environments.
Finally, I would like to introduce the pressure temperature ratings table for ASTM, the 351 grade CF8M and CG8M valves. This table summarizes the ratings for CF8M and CG8M valves belonging to the standard class, specifically the two materials marked as Note 1, and the rating criteria follow the ASME B16.34 standard. CF8M is a cast type 316 and has the widest temperature range, from -425 to 1,500 degrees Fahrenheit, while CG8M is a cast type 317 series and is magnetic due to its ferrite content. The table provides the allowable working pressure for each class and temperature in both SIG and bar units.
Now I would like to introduce the pressure temperature ratings table for cast type 316 stainless steel, namely ASTM A351 grade CF8M and CG8M valves. This table follows the ASME B16.34 standard and summarizes how the allowable working pressure of the valve decreases as the temperature rises. Looking at the table, 3 pressure values appear as a group for each temperature row, which correspond to different pressure classes. For example, in the low temperature range, it starts with values like 1240, 1860, and 3095 sig. As the temperature rises, these drop to 1120, 1680, and 2795, and then further down to 1025, 1540, and 2570. You can see the trend where the allowable pressure decreases stepwise as the temperature increases. In the high temperature region, it drops further, such as 1160 to 1930, 1050 to 1750, and 1030 to 1720 sig. At the highest temperature end of the table, it drops to 20 sig, or approximately 1 bar. Please keep in mind that this region applies only to welded end valves, and flanged end ratings terminate at 1000 degrees Fahrenheit.
Along with the conclusion of the pressure temperature ratings table for CF8M and CG8M materials, I would like to introduce cast iron valve materials. First, you should remember that the upper usable temperature limit for CG8M is limited to 1000 degrees Fahrenheit, or 538 degrees Celsius. Although it is included in the same table, its heat resistance limit is lower than that of CF8M. This ratings table follows the ASME B16.34 standard, and some values in the table apply only to welded end valves. For flanged end valves, there is a proviso that the ratings terminate at 1000 degrees Fahrenheit. Next, I will introduce cast iron materials. Cast iron follows the ASTM A126 standard and is an inexpensive, non-ductile material, meaning it is brittle. For this reason, it is used to control steam, water, gas, and non-corrosive fluids rather than for high-pressure or high-impact applications. The pressure temperature ratings for cast iron valves are determined according to the ASME/ANSI B16.1 standard.
I would like to introduce the method of categorizing the pressure temperature ratings of cast iron valves based on the nominal pipe size. The cast iron valve ratings table is organized for the nominal pipe size range of 1 to 12, or NPS 1 to 12. The temperature application range is based on the interval from -20 to 150 degrees Fahrenheit, which is -29 to 66 degrees Celsius. As mentioned previously, cast iron is used for controlling steam, water, gas, and non-corrosive fluids. Meanwhile, the pressure temperature ratings table for CF8M and CG8M materials continues on the same page, and this table also follows the ASTM B16.34 standard. The rating values for each class are listed separately by nominal pipe size and temperature interval.
I would like to introduce the system for categorizing the pressure ratings of cast iron valves according to class and nominal pipe size. The ratings for cast iron valves are largely divided into two grades, Class 125 and Class 250. The material standard is ASTM A216, and it is further subdivided into Class A and Class B. The nominal pipe size is applied separately for the NPS 1 to 12 range and the NPS 14 to 24 range. Even within the same class, the allowable pressure varies if the nominal pipe size range is larger, so rating values for each nominal pipe size interval are provided separately for Class A and Class B. This ratings table follows the ASME/ANSI B16.1 standard, as previously mentioned.
I would like to introduce the table that compares Class A and Class B for ASTM A216 cast iron valves based on temperature. This figure is structured to place Class A and Class B side by side, allowing for a comparison of their respective allowable pressures according to the temperature interval. In other words, since the rating values for Class A and Class B differ even at the same temperature, it is used by first checking the temperature of the operating conditions and then reading the pressure value for each class from the corresponding column. Please also remember that the pressure temperature ratings for cast iron valves are based on the ASME/ANSI B16.1 standard.
I would like to conclude the cast iron ratings table and transition to cast bronze valve materials. In the Celsius and bar conversion sections of the cast iron ratings table, there are many items marked with dashes where data is empty. This means that ratings for those specific temperature and unit combinations are not separately defined. Next, the material changes to cast bronze. Cast bronze valves follow the ASTM B61 and ASTM B62 standards, and the pressure temperature ratings are based on the ASME B16.2 standard. The units in the table are configured with Fahrenheit and Sig, as well as Celsius and bar, listed together. Bronze is generally a material suitable for low pressure, low temperature, non-corrosive service.